Hi, my name is James Anderson, and I'm a researcher at the Air Force Institute of Technology located in Dayton, Ohio. I'm here to talk about our work into the Delaunay Walk for fast nearest neighbor matching. Point set registration represents a challenging problem for numerous applications, including computer vision, pattern recognition, robotics, and image processing. Registration finds a transformation between two or more data sets, providing a rotation and translation that minimizes the difference between corresponding pairs of matched points. These point clouds can be known in advance or generated from images, LiDAR, or other sensors. A common point registration method, Iterative Closest Point, or ICP, typically must execute in near real time. In self-driving cars, onboard computers may utilize the transformation found by ICP to detect objects within the car's local environment and need to take immediate action. ICP is broken into three major steps: nearest to neighbor search, transformation estimation, and transformation validation. After investigating these steps, the nearest neighbor search consumes at least 90% of the processing time. For this reason, our research focuses on accelerating the nearest neighbor matching employed by point set registration. Nearest neighbor matching finds a point in a reference point cloud, seen here in red, nearest to a corresponding point in the sensed point cloud, seen in yellow. ICP then takes these neighbor pairs and calculates a rotation and translation to minimize the distance between the pairs and better align the two sets of points. Since the first step takes the majority of the time, applications typically utilize a space partitioning structure such as a KD tree, R tree, or Oct tree. Searches of tree structures typically remove the need to compare the query point to every other point, greatly reducing the time required. Our work uses the Delaunay triangulation. In 2D, a Delaunay triangulation connects the points into triangles such that no points are located within the circles created by the vertices of each triangle. When extended to 3D, the triangles become tetrahedrons and the circles become spheres. Shown here is the full Delaunay triangulation of a 3D point set. Each line represents an edge of one of the triangles in the Delaunay. And here we visualize a closer view of all the edges connected to a single point, shown in pink, connecting to its neighbor points, shown in blue. A search for the nearest neighbor using the Delaunay can start at any point. If the query point is closer to any of the points connecting to the starting point, we walk to that point and restart the process. Once we reach a point with no other closer points, the search can stop with the last point the closest. The main advantage to this approach is being able to start from any point. In other methods, you have to start at the root of the data. With the Delaunay walk, the search can start from anywhere. Each iteration of ICP moves the points slightly toward the target. Since the points move gradually each iteration, the new neighbor points should be close to the neighbors in the previous run. We can use the previous neighbor as a starting point and likely not have to travel far. Our research shows when starting from the previous neighbor, it only takes on average 1 or 2 walks to find the new closest point. That number is also independent of the total number of points. The main takeaway is the Delaunay walk greatly accelerates the search from requiring to search a tree from the top to bottom to only taking a few steps along the Delaunay edges. To test our algorithm, we compared our methods to the traditional ones. We implemented our algorithm in C++ to run on a CPU and in CUDA to run on a GPU. Our experiments found using the Delaunay method along with the previous nearest neighbor increases the runtime at least 10 times. To show our methods in an application, we applied our ICP with Delaunay traversal to a stereo vision pipeline. The first part of the pipeline is stereo block matching, which generates 3D sensed points from features within the images. Next, ICP fits those sensed points to a known reference point model, resulting in the position and orientation of the object. In a motion capture chamber, we conducted a simulated approach of a scale model aircraft. The accuracy of the stereo vision pipeline is verified by comparing to the truth data from the motion capture system. This video shows a virtual rendering of the motion capture room. Where the red, blue, and green lines converge is the origin of both the virtual world and the motion capture system. The yellow points seen on the right are the result of stereo image processing, and the red points are the result of ICP determining the position and orientation of the aircraft. The upper corners play back images captured from real cameras in sync with the motion capture. The red cylinders in the left center of the screen depict the location and direction of the cameras in the actual room. To validate their position, virtual images are rendered in the bottom corners of the screen. As seen in the output at the bottom center, Our algorithm enables the pipeline to run at around 20 frames per second. In previous work, a typical speed was around 10 frames a second. Now, with our accelerated ICP, the stereo vision pipeline is twice as fast. Being faster allows us to process more points, and more points improves the accuracy of the output. Even further acceleration is possible by reducing the number of iterations of ICP and parallelizing stereo block matching with a graphics processor, both of which we look forward to doing in the future. Thank you for watching our video. We hope you learned a little bit about point registration, ICP, and nearest neighbor matching.